All right, the recording has started.
So, hello everyone. Welcome to our point distribution webinar. Our today's speaker is Ruiwen from University of Maryland, and he will talk us about dynamicals of particles on a curve with pairwise hypersingular repulsion. And after the talk, we will have, as usual, some time for socialization. So please, if you would like to talk with people, just stay stay in Zoom. Ruben, please.
Okay, thanks for the introduction and thanks for the invitation. It's really my great pleasure to speak here. Today, I'm going to discuss my recent work with Douglas Hardin, Edward Saff, and Eitan Tadmore on the dynamics of a large group of particles restricted on a curve with pairwise hypersingular repulsion. So let me first introduce the model. So our underlying space is the following. We have a smooth, closed, non-self-intersecting curve, which is in RD. So you just imagine that you have a very nice curve. So it can go back and forth, but never do self-intersections. And if you look at each point of the curve locally, it just behaves very nicely. Let me denote this curve as vector x of z, and then since it is a closed curve, we just use this kind of periodic boundary condition, and we also normalize the total length of the curve to be 1, and we use a curve length parameterization for the curve. And then we assume we have capital N moving particles on the curve. So all the particles are just restricted on the curve. And their location are just given by the parameters along this curve called Zi here. So the location of the particles are just vector x of Zi for I from 1 to n. And each Zi is a function of the time variable t. So they are moving on the curve. And the dynamics of those particles is given by this first order ODE system. So here you see that the time derivative of each Zi is given by a forcing term. So now we are doing a first order dynamics. So it is just the first order time derivative here. And the forcing is on the particle I is that for all the other particles J, you have a pairwise repulsion between the two particles. So let's say, suppose this is the particle I and this is the particle J. So they have a pairwise repulsion whose direction are along their connection segment. And then the strength of the repulsion is given by a radial potential, which is this kind of raised type. So we just have a power law like x norm to some power minus s over s. So this form guarantees that it is always a repulsion for whatever values of s. And then you see, generally speaking, the direction of the forcing may not be along the tangential direction of the curve. So to restrict every particle on the curve, what we did here is that we just do a projection onto the tangential direction by taking an inner product with a unit tangent vector x prime. And then we just sum up over the forces from all the other particles and get the total forcing on the ith particle. So here you see we have a scaling here, which somehow makes it has some nice scaling when you take the n number of particles be really large. I will explain this later. And here, let me mention that we will focus on the case when this power s is greater than 1, which is called the hypersingular range. So generally speaking, when you are restricting particles on an m-dimensional manifold, then s greater than m is called the hypersingular case. Here, we are just taking a one-dimensional underlying space. So later I will explain why this hypersingular is this number being the dimension is a critical power here. Okay, so to understand the dynamics of this particle system, I think we could start from the total energy. So the total energy is just a summation of all the pairwise interaction energies. And then this particle system, this ODE system is just a gradient flow of this total energy, saying that if we view all the particle configuration as a whole space, then in this R capital N, you just have a gradient flow like a capital Z dot is equal to minus gradient of the energy. So following from the gradient flow structure, you see that the energy of the system is always decreasing with time. And one can write down the energy dissipation law explicitly by saying that E dot is just like minus the sum of all the particle velocities squared. So whenever you have particles moving, then the energy is always dissipating. So for a gradient flow, the expected lifetime behavior of this particle system is just, you see, you have a total energy, which is always decreasing. And also, this total energy is always positive, just by definition. Then you see, we can expect that as t goes to infinity, the total energy will converge to some limit. And also in nice situations, we will also see that the particle configuration will convert to some local energy minimizer. So here it is important to notice that generally speaking, this energy function can have a quite complicated topography. So there could be many local energy minimizers. And for a gradient flow, it often happens that it is just trapped into one of the local energy minimizer instead of going to the global minimizer. Okay, so now let me explain what's special about this power s equals 1. So suppose we take a power s less than 1. For example, let's just try if s is equal to -1. Then we just have a negative absolute value x, which is not very singular at the origin. In this case, one can just at least on the formal level, suppose when the particle number n is getting very large and the particle is very well described by some particle density function rho, then it's natural to derive a formal continuum limit as the following. Instead of having a double summation here, now you just have a double integral in the locations y and z, and with the weights rho of y and rho of z here have the potential. So in this integrable case, where I mean this w is at least a locally integrable function, in this case, at least on the formal level, one can derive a continuum limit of the total energy. So in this case, I think when n is getting very large, from a modeling perspective, a better way to analyze what's going on is just to use the continuum formulation, saying that now we have some energy function on a density function rho, and then one can formulate the dynamics as a Wasserstein-2 gradient flow, which is a transport PDE for this particle density function. So that's a different story. So what I'm going to focus on today is the hypersingular range when the s power is greater than 1. So in this case, you see, suppose I look at this 1D energy function. Now, if W has the power s greater than 1, then this part is no longer locally integrable. And even on a formal level, this energy function now is no longer well defined. So in this case, the question is, what should be expected when n is getting large? First of all, what should be the energy minimizers, either local or global? And also, what should be expected for the lifetime behavior, since now we cannot use any continuum limit, basically. Okay, Now let me just introduce some ideas from the previous results. The first one is on the energy minimizer. This is the so-called poppy seed bagel theorem, which is first proved by Hardy and Seth in 2005, and later refined by Borodachov in 2012 in the 1D case. This theorem says the following. Suppose we have a hypersingular raised energy, just this kind of power negative S energy, of an m-dimensional rectifiable set. This is just some generalization of an m-dimensional smooth manifold, just with less regularity. Then in this case, suppose you just put n particles onto the manifold with this hypersingular repulsion energy. Then the global energy minimizer has a nice description. They prove that it is almost a uniform distribution when n is getting large. So as for n is getting larger, then the particle distribution is getting closer and closer to a uniform distribution. You see here, this is a particle simulation from their paper. What they did is a manifold with dimension m equals 2. Actually, this is how the name of the theorem comes from. It just looks like this torus, which looks like a bagel, and you are putting some poppy seed onto the bagel, something like that. Okay, so in their simulation, suppose they take a power s equals 0.1, which is less than the dimension m equals 2. Then you'll see the energy minimizer look like this case, where there are some vacuum region and some particles are very densely packed on the outside of this manifold. So this is clearly not a uniform distribution. If you increase the power s a little bit, still less than m, then you see now there is basically no vacuum region, but it is far from uniform. Outside there are more particles, and inside there are less particles. But once you get to the critical value s equals 2, or a higher value of s, you see that the pictures are not really very different. You basically just see this uniform distribution of particles. So this is what the theorem means. So now, if we care about our dynamics, we said that we expect the particle configuration of our particle dynamics on a curve to converge to an energy minimizer. So this theorem at least tells us that the global energy minimizer should be an almost uniform distribution. So one expectation is that maybe for our dynamics, as t goes to infinity, our dynamics should converge to almost a uniform distribution. Okay, so the next result is about a mean field limit for this particle dynamics, which is our system with the number of particle n goes to infinity. This mean field limit, although I still calling it a mean field limit, is actually very different from the integrable case. Because in the integrable case, you can just write in the most formal way and get it. And when your W has enough regularity, you can justify that rigorously. However, for this hypersingular case, even a formal derivation of the mean field limit is not so straightforward. So here in the hypersingular case, you'll see this W, if the power s is getting large, then the repulsion becomes very strong when your distance is short. That is, each particle basically just feels the repulsion from several nearby particles. And once the distance is getting a little bit large, then the repulsion is negligible. So in this case, we could say that the interaction becomes essentially local when it's getting large in the hypersingular case. Okay, so if this is the intuition, then of course we don't expect some energy functional like this, because this energy functional in the integrable case is a global energy functional. You see different locations are really connected. But now, since the repulsion is essentially local, we expect that in whatever sense, the total energy should also become a local functional if you take n goes to infinity. Okay, so again, we describe as n goes to infinity, when try to describe the particles by a particle density function rho, which depends on the time and the spatial locations. And there is a previous result on the mean field limit by Oschlager in 1990s, saying the following. So suppose we are just on the real line, one-dimensional real line, then as n goes to infinity, this particle density function should solve the porous medium equation, where here this power is just related to your repulsion power S. Okay, so now I'm not going to discuss the detail of the proof, but let me give you some intuition, which will also be useful for our result. So the intuition is like the following. We have said that as n goes to infinity, the repulsion should be effectively be very localized and also very strong, because the repulsion is very singular to the origin. And the intuition is that such kind of strong local repulsion should enforce the particles to be locally uniformly distributed. So this is a typical picture of a locally uniformly distributed particles. So you see, suppose you just look at this interval, then the particle just look like a uniform distribution, very close. And if you just look at this region, then it also look like uniformly distributed. But if you take a global picture, then you see that the density of the particles are changing gradually on a very large scale. So this is what I mean by a locally uniform distribution. And then when n is getting large, there should be some well-defined notion of a macroscopic density rho of z, rho of the location. So you see here, you should have the situation when rho is getting large, and here you should be a smaller rho. Okay, so I think this kind of picture is kind of comparable with the kinetic theory, where you have a particle density function with both the spatial and the velocity variables. Then the local, this kind of local equilibrium, saying that you achieve an equilibrium in the velocity direction, but in the spatial location, you still have some macroscopic variation. So now it's just like somehow the velocity direction and the spatial direction becomes just the same axis, but on different scales. So on the small scales, you see the local equilibrium, but on the large scale, you'll still see some variation of the density. So suppose we are in such a situation, then let's analyze what's going on with the total energy. So you see that this is the total energy. Suppose we just consider those contributions for those particles Ci in some interval, capital I, with mesoscopic length, which means it is relatively small comparing to other one, but it still contains quite a lot of particles. If you compute this, then you can say that, okay, in this short interval, you should be basically a uniform distribution with some density rho evaluated near this point. Then this means the distance between Zi and Zj, suppose all the particles are following the order like from Z1, Z2, Z3, and so on, then Zi minus Zj is basically just the typical spacing times I minus j, and the typical spacing is just 1 over n times rho. So if rho is larger, then the typical spacing is smaller. Then you're just replacing this by the quantity from the uniform distribution with this density rho. And then you see that this scaling is exactly the scaling which makes this whole summation becomes order 1 quantity. So now it's important to notice that s greater than 1 guarantees that this series is convergent. So when you have a lot of particles in this interval capital I, it's reasonable to just approximate this by an infinite summation, which is also a finite number. And you compute that, this actually gives you rho to the s plus 1 times the length of the interval. So now if you take a summation over all the short intervals I, then this basically becomes just an integral of rho to the s plus 1. So this means, at least in this nice situation, the total energy is just like some kind of internal energy, which is localized. And now an intuition is that originally you have a gradient flow of the particle energy. Now, as n goes to infinity, you expect the particle energy becomes the internal energy of like this for the density function. Then you expect that on the continuum level, the dynamics of rho should also be a gradient flow of this internal energy, which is exactly the porous medium equation. Okay, so now let me formulate our result. So our result is completely on the discrete level, which is formulated as the following. Suppose you take any epsilon greater than 0, which is the extent to which you want to get close to the uniform distribution. Then, depending on this epsilon, there exists some large capital N0, such that as long as your n is greater than that, you have the following conclusion about the dynamics. If you wait for a long time, like order 1 over epsilon, then you will see that the total energy will decrease to a level which is the optimal energy. This zeta tilde of s as defined on the upper corner of the slide. One can compute that just as the optimal, the minimal energy if you just imagine you have a exactly uniform distribution. Then the energy will decrease to this level times 1 plus epsilon if you wait for long enough time. And you see this gives a convergence rate as t goes to infinity, which behaves like capital O of 1 over t. And it's important to notice that this convergence rate is independent of the number of particles. So this estimate is still effective even if you take your n to be very, very large. Also, we proved that this convergence of the energy will imply that the particle configuration is converging to the uniform distribution in the following sense. Suppose we just take any interval on the torus, and then we count we count the number of particles inside this interval and normalized, and take a difference with the interval length. So suppose you have a uniform distribution, then this quantity should be equal to 0 if your interval are at the particles endpoint. And now we are saying that this difference is small. It is controlled by some order epsilon to the power 1/2 quantity. So this tells you that once your T is getting large, then your particle configuration is converging to the uniform distribution in such an average sense. Okay, so what's the main difficulties of proving such a result? So I think the first difficulty is that although we know the global energy minimizer should be an almost uniform distribution, at least right now, before our result, we don't know whether local minimizers are also having almost a uniform distribution. And the gradient flow could be trapped into local energy minimizers, or even worse cases, you may be trapped at the saddle points. As far as we know, if you are taking multi-dimensions, then saddle points can be non-uniform distribution. And we also guess that a local energy minimizer could also be non-uniform distribution. So in this case, this 1D case is quite special because in the 1D case, our theorem says that you just cannot have any local energy minimizer or saddle points which are not almost a uniform distribution, because our dynamics, if we start from a local minimizer, it just stay there. If our theorem is true, then you'll see it has to be almost a uniform distribution. Okay, so this is one tricky point about the local energy minimizers. And the next difficulty is that maybe you think, okay, we already have a mean field limit at least on the real line. Maybe that's not too far from getting one on the curve. And you want to apply a mean field limit and use whatever conclusion from the continuum from the continuum equation for the large time behavior. However, this kind of approach cannot work because, generally speaking, mean field limits are always finite time results, which says that although the error of the mean field limit, if you take a finite number of n, is generally small when n is getting large. For example, suppose you have an error like 1 over order 1 over n. This kind of error often grows exponentially in time, which basically means that the error of the mean field limit, I mean the difference between the discrete model and the continuum model, is basically behave like 1 over n times e to the power t. So if you care about a large time behavior, then when the t is getting really large, it will eventually win the 1 over n, and then the mean field limit is no longer accurate if you wait for long enough time. Okay, so this means if you want to rigorously prove such a large time behavior for the particle system, then you cannot apply the mean field limit directly. So another difficulty is some complication from the curves, because as far as I know, if the curve is exactly a circle or very close of being a circle, then the W restricted on the curve will just become a convex function, and the large time behavior will be much easier. However, when the curve shape is getting very complicated, then you just lose this kind of convexity. And in this case, you basically cannot rely on any convexity argument directly on the original energy function. And in this case, we have to do some different argument here. Okay, so now let me discuss our strategy of proof. So I think this proof is largely motivated by the mean field limit of the system as a porous medium equation. So the first thing is that the interaction between the particles should be essentially local, because we are in the hypersingular range. So our idea is to say that all those errors from the all those curvature effect, like the difference between a straight real line and the curve, should be just should just be some error term. You just need to estimate how large they are and finally discard them. They will not play an important role in the large time behavior. So that's the first intuition. And the second intuition is just now we try to focus our intuition on the real line case, and then get intuition from the mean field limit. So our idea is that we try to write down some way of proving the large time behavior for the porous medium equation. And we try to find such a way so that we can find an analog on the particle level. So there are many different ways of proving the large time convergence of the porous medium equation to the uniform distribution. We tried a few of them, but finally, I think this is the only one that works. So our idea is first to analyze the total momentum of an interval of mass. And then once that, we combine that with the maximal principle for the porous medium equation. And this procedure on the porous medium equation, it gives you a large time convergence to the uniform distribution. And on the particle level, it has an analog. Okay, so now let's first get the intuition from the porous medium equation. We first write it into the form of a transport equation, where you see write this second derivative as like a spatial derivative times a spatial derivative of rho times some transport velocity. Here, negative of this quantity is exactly the transport velocity in the porous medium equation. And then we just compute the total momentum for some interval of mass, namely here. So we just take an integral of the transport velocity times the weight function rho and integrate on this interval. This is the total momentum, and if you write this part partial z rho to the s times rho into a perfect derivative, then it just becomes rho to the s plus 1 minus rho to the s plus 1, taking a difference at the two endpoints. So see, suppose we have two spatial locations, I'm calling it ZM, ZS, where at ZM, rho achieves the maximum, and at ZS, rho achieves the minimum. Suppose this is the case, and the rho at these two locations have a significant difference. Then you'll see that this term is much larger than this term. So we get a lower bound on the total momentum. Okay, this means that in our porous medium equation, if we just view all of those red mass as a whole bulk, then this whole bulk is moving. No matter what kind of inner motion you have, this as a whole bulk, it is moving. So it's quite intuitive because you can imagine this kind of porous medium diffusion as a pressure. So you see at here, you have a large density, so the pressure is large here, and the pressure here is smaller. So this whole bulk is definitely pushed to the right. Okay, and actually this lower bound of the total momentum will help us obtain a lower bound on the energy dissipation rate. So if you write down the time evolution of the total energy, then you get something like this, which is velocity squared times rho integrate. And you use the Cauchy-Schwarz on this, you will obtain a lower bound of the energy dissipation rate as the square of the momentum over the total mass. So if you have a lower bound on the momentum on some interval, then this will give us a lower bound on the energy dissipation rate. Okay, so here comes the point. Suppose your density always have this kind of variation at a maximum and at a minimum, you have a significant difference. If this is the case, then you always have a lower bound on the energy dissipation rate. However, you only have finite amount of energy to use. So finally, the energy will exhaust itself, and you cannot have this energy dissipation rate as large as this one for all time, which means once you wait for long enough time, then the rho here and rho here have to be close with each other. So in this case, once you see such a state for some time spot, then you can apply the maximal principle, because once the maximal density is getting small, getting close to the density of the uniform distribution, then it just cannot become large again. And this is how you can guarantee that such an almost uniform state will propagate in time for all time later. Okay, so this is the intuition from the continuum, and now let's discuss how to find a particle analog of that. So our first part is the so-called total repulsion cut, which is some kind of analog of this term. That is, what is the pressure when you have really low density here? Okay, so to simplify the situation, we just put it on the real line, and later on when we put it on the curve, we just approximate by the real line together with some higher order error terms. So suppose we have some particles x0 to xn on the real line, and for simplicity, we just normalize them as the left endpoint is 0 and the right endpoint is equal to 1. So suppose we have two particles xk and xk plus 1. We define the total repulsion if we cut here as this pk, which is just the summation of all the repulsion forces between the left and the right. So see, we take I as on the left, J as on the right, and we compute the total, we compute the repulsion force and take a summation. Okay, so if you imagine this as a whole bulk and this is another, then this is just the repulsion of the two bulks of particles. So our lemma says the following. For any epsilon, suppose n is large enough, then you can always find some index to cut such that the total repulsion between the left and the right is bounded above by a constant bounded above by 1 plus epsilon times whatever it should be for uniformly distributed particles. Okay, so you see in our continuum situation, we just want to find somewhere to cut such that the pressure is small. So this lemma says that for whatever kind of particle configuration in this interval, you can always find a place to cut the particles into two bulks such that the pressure here is just no larger than 1 plus epsilon times the uniform distribution case. So in the uniform distribution case, you can just follow the formal mean field limit and see that it is basically the same situation as a continuum. So this tells you that in a discrete setting up, you can always find a location so that it is not worse than the continuum case. And also we have a requirement that this cutting point is not too close to the endpoints, which is just some technical requirement. Okay, so I think the proof of this lemma is the most elegant part of this paper. So what we did is a min-max type argument. So first of all, since we don't want to be close to the endpoints, we just fix all the particles in the endpoints, and we will the minimum of all the possible cuts in between, like we just take the minimum of all the pk as some function of all the particle configuration in between. Okay, so now you see that since we want to find some place to cut so that the repulsion between left and right is as small as possible, whatever particle configuration, we just use the minimum of that, right? Okay, so if you reduce the minimum of that, we want to analyze what's the worst possible situation for our minimum of the repulsions. So then we care about what is the maximum of this function of Fm as a function of the particle configurations. So the conclusion is that the maximum of this Fm is unique, and it is achieved at the same point as the minimizer of an energy function, which looks like this. We just look at all the pairwise interaction energies, and then we view them as we view it as a function of the particle configurations in between. Okay, and this maximum coincides with this minimum, and they are characterized by just all the repulsion at each cut point is exactly equal. Okay, so now let's see why this actually simplifies the situation, because the maximum of such a minimum function, this is quite complicated to understand. However, this energy functional is actually quite nice, because you see that this functional is actually a convex functional. So you know that this energy functional is unique, and it is achieved at the gradient of the energy is equal to 0. If you compute that, you get exactly this condition. So you see, at least this implies the uniqueness of the maximum of Fm, which is a non-trivial fact. And then once you have this, you can use this condition, this energy minimizer condition, and the Poppy-Seed-Bagel theorem type argument to say that, okay, this unique minimum as an energy minimizer has to be close to the almost uniform distribution. And then it tells you that the maximum of this is also achieved at almost uniform distribution. And we know in this case that if we have almost a uniform distribution, then this is exactly the number one should get. So up to some error, just get this inequality. Okay, so why this maximum of Fm also have the same characterization condition? Let's just try to understand this. Suppose this condition is not true, then you have some location where the repulsion pk at here is greater than the minimum of all the pk. Then you can do the following. You just move these two particles a little bit outwards, so that you can analyze that once you do this kind of movement, then the total repulsion at here is decreasing, and the total repulsion at every other place are increasing. So if here you don't have the minimum value of the pK, then you see the total minimum will be increased, so that it contradicts with the maximal assumption of this configuration. That means for whatever maximum of Fm, it has to satisfy this characterization condition. Okay, so this is the first part, how we find a place to cut with a very small pressure between the left and the right. And the next thing is an analog of the maximal principle. So in the Paul's medium equation, we know that the maximum of rho of t of rho of x never increases. So an analog of the maximal density is the following quantity, which is the closest pairwise distance, and we denote it as delta of t. So basically, if you take 1/n times delta of t, then this is an analog of the maximal density. So our lemma says that you have the time derivative of delta is greater than a very some negative quantity, and the absolute value of this is very small. So basically, you can just imagine that here we have ddt of delta is greater than or equal to 0 up to some error which is small when n is kind of large. Okay, so this almost says that the maximal density never increases. So this is just an analog of the maximum principle of the Paul's medium equation. Okay, and also we have a stronger version saying that, in that situation, if you are following the mean field limit, then the maximum density could decrease, but should decrease in a reasonable rate. It shouldn't be decreasing too fast, faster than order 1 rate. So suppose this maximal density is decreasing too fast in the particle level. That is, if that is on the particle level, if your delta is increasing too fast, then that's kind of a very special case. Suppose we are not in that case. That is, if we assume ddt of delta is not too large, then in this case, we claim that if we look at this location where the closest distance is achieved, we call it IM, then the total repulsion, if we cut at IM, is bounded below by 1 minus epsilon times whatever one should have for the uniform distribution. Okay, so that tells us that if the maximal density is not decreasing too fast, then basically the total repulsion at IM is as large as the continuum case, so that we can just recover this term, this large pressure term in the continuum case. So of course, there is an exceptional case what if maximal density is decreasing very fast, but this case is already helping us because if maximal density is decreasing very fast, then it will get to a small value in a short time. But the previous lemma tells us that once it gets the maximal density is getting small, it cannot go back again. Okay, so now let me discuss how to prove these two lemmas. So the idea is the following. Suppose we want our delta to be either decreasing or stay the same value. Then what could be the best way of the other particle configurations to keep this delta not increasing? So since this delta is already the closest pairwise distance, and the two particles CIM and CIM plus 1 has a very strong repulsion between them. So if you don't want the distance to increase, then the only way is you just try to pack all the particles close to this pair as much as possible. Since delta is already the smallest pairwise distance, the densest you can pack is that every pair has a distance delta. And in this case, you actually have a locally uniform distribution here, which recovers the continuum case. And in this case, you know that the maximal density should just stay constant. In other words, the delta should stay constant in this case. Okay, so that basically tells you that ddt of delta is always greater than or equal to 0, up to some error from the curvature effect. And also, suppose you are not at this, not exactly at the uniform distribution nearby. Suppose you have some kind of defect which destroys the uniform distribution structure. Then you can compare this with the uniform distribution case and say that once you have a defect, then the delta has to increase. So this increase will break this condition. So in other words, suppose you have this delta not increasing too fast, then you have to have a locally uniform distribution near this ZIM point. And then according to the derivation, the formal derivation of the mean field limit, you can show that this repulsion according to almost a uniform distribution should just behave like whatever you will see in the continuum case. Okay, so finally, we still need to handle the curvature effect, and this part I think is quite technical, and let me just formulate the lemma a little bit. So basically, when we have a forcing from z to y, that is this forcing projected onto the unit tangent vector at y, then this is approximated by the forcing on the real line. That's the double prime y minus z. And also there is a correction term from the curvature effect where this kappa of y is just the curvature at this point, and this is like a second order correction here. And once you take this forcing with approximation here, then you get just some higher order error. And we can even do that if we try to compare the two errors at y and y tilde, and we can gain a term like y minus y tilde here. So the proof is just by some very complicated Taylor expansion, so that I'm not going to discuss here. So this is like whenever we have some quantities on the curve, the forcing like this, we just use the approximation and put all the errors together, and finally we can show that the error will be small enough. Okay, so finally, for the proof of the main result, we just do whatever the same thing we did for the porous medium equation as a particle level analog. So suppose we have two locations where here the density achieves the maximum, that is the ZIM. And we also look at the other another interval so that the density is just approximately equal to 1, which is a uniform distribution density. Okay, suppose here we have a larger density, then by our previous lemma, suppose our maximal density is not decreasing too fast. Then in this case, we know here near IM, we have almost a uniform distribution, so we have a strong total repulsion here between the left and the right. And also we use the first part to get some point IS, such that here, since we have a low density region, we can find a location to cut it so that the left and the right have very small repulsion between each other. So that if you can consider all the parts in the middle as a whole bulk, then this part is pushed to the right, just following the green arrow. So this means that if we take the summation of all the zi dot in between, then this will have a lower bound in terms of the rho m, the maximal density. Okay, so and then similar to the porous medium equation, this provides an energy dissipation so that this cannot last forever. And then to close the estimate and finally get energy an explicit convergence rate in time, what we have is just something like the E is also controlled by the maximal density. So you can imagine that if the maximal density is getting close to 1, then the whole distribution have to be close to almost a uniform distribution with density 1. So this is how we get the exact convergence rate as t goes to infinity. And here, for the exceptional case, when the density is indeed decreasing too fast, then what we do is to construct a Lyapunov functional by adding e with some multiple of the maximal density to a power, something like that, so to take care of this exceptional case. And finally, let me just discuss a little bit how the energy convergence implies the particle configuration convergence to the uniform distribution. So this is a direct consequence. This particle configuration convergence is a direct consequence of the energy convergence. So here our idea is to include some functional called EK, which is just all the energy from the pairs like Zi and Zi plus K, so that you can decompose the total energy as the summation of all the EKs. Once you have this, then you reduce it to the real line case to analyze the energy. And then our lemma says that all our EK tilde are just bounded below by whatever you should have for the uniform distribution, just by a convexity argument. So this, together with our assumption on the total E, gives us an upper bound of the E1, just all the energy contributed from adjacent particles. So then this E1 is just a summation of W of the Di, where you just have Zi plus 1 minus Zi. And then you just do a Taylor expansion of this E1 for this W at 1 over n, because you know this each Di should be 1 over n for the uniform distribution case. Once you do that, you will see the first order Taylor expansion is canceled, and you'll see a second order Taylor expansion, which gives you the Di minus 1 over n. And here we use the convexity to say W double prime is always positive. So you'll see this red box is bounded above by some order epsilon. This gives the smallness of the Di minus 1 over n up to the order square root of epsilon. Okay, so finally, let me briefly mention some possible future work direction. First of all, we actually expect the optimal convergence rate should be exponential, because in the porous medium equation, if at some moment rho becomes bounded from below, then the diffusion is no longer degenerate and you will recover exponential convergence rate. So right now, the best we can do on the particle level is a 1 over t convergence rate. And we are wondering whether we can improve that to exponential rate. Another direction is that once we know the lifetime behavior on the particle level, which is independent of n, then we care about whether we can prove a uniform in time mean field limit. This is somehow like for short time, we have the original mean field limit, and we need to generalize that to the particle case, to the particles on a curve from the original particle on the straight line case. And then one can try to connect such kind of short time mean field limit with a large time behavior to get a uniform in time mean field limit. That might be possible, I think. And another direction is from some numerical simulation where we saw that actually, even if you start from some random distribution initially, then the particles always converge to some local equilibrium, that kind of local uniform distribution in a very short time. And at a larger time scale, it's actually just following the continuum limit. So we are curious whether we can prove this kind of short time local equilibration in a rigorous way. And of course, one can ask the question about extension to multi-dimensions. I think due to the difficulty of local energy minimizers and set points which may not be the uniform distribution, we still don't have any idea on this direction. Okay, that's all for my talk. Thank you.
Thank you very much. Very nice talk. Please, questions.
Yeah, so thank you for the nice talk. So could you go a couple of slides back? Yeah, no, sorry, that's too many. I literally meant 2 slides back from the end. So you get an estimate on the distance. So you get some estimate on the discrepancy between the density and
you mean
yeah, right here. Yep. Yeah. So that's basically, so you're basically estimating. So that's an estimate on the discrepancy of your configuration in terms of let's see, in terms of the difference. Right. Yeah. Okay. So this is actually quite nice, right? So you get an estimate on the discrepancy in terms of the difference of energies.
Yes. So when the energy is getting close to the optimal energy, then what we first proved is something like the summation of di minus 1 over n is of order square root of epsilon. And then this implies this.
So that's like square root of the difference of energies. Exactly. Yeah, exactly as it should be, because so if energy defines some sort of distance on, well, at least for s less than d, for instance, it would be just distance on the integrable distributions, right? Yeah. So you mentioned that you don't expect this to be true for higher dimensional distributions. So what's your guess? What's the local minimizer that is bad in high dimensions?
For example, suppose you are taking a sphere and you just put all the particles along a big circle. Then due to symmetry, the dynamics will never leave the big circle. You will just have a uniform distribution on the circle instead of going to the whole sphere. So I think this is kind of a saddle point. So I think for local minimizers, whether there are local minimizers which are not almost a uniform distribution, right now I'm not sure about the true fact, but one of my collaborators tells me that he believes there should be such strange local minimizers. So we are still trying to work on these directions. So actually, whether there are such strange local minimizer is, I think, itself an interesting question.
Yeah, so it's interesting that it's a purely degree of freedom thing, right? So in 1D you have 1 degree of freedom, and so you apply you move points around and you always arrive at a uniformly distributed minimum.
More questions, please.
Earlier, so this all was focusing on the hypersingular case, and maybe you did say this in the beginning, but so in the integrable case, do you also expect that dynamics would lead to uniform distribution at a similar convergence rate, or
no? In the integrable case, we don't even expect the global minimizer to be uniform distribution. You see, this kind of thing could be a global minimizer.
Sure. I guess I was just wondering if that was also the case in like the one-dimensional one-dimensional curves.
In the one-dimensional case, I think an integrable case would still give an energy minimizer which has not uniform distribution.
So if it's a circle, you do get uniform distribution, but if you deform the
Oh, sure.
then you just imagine that if you are in the integrable case and you have an ellipse which is very long, then you look at this energy integral. So since the particles are very repulsive, you expect that the particles are more concentrated at the two long ends of the ellipse.
Sure, sure. No, I was definitively picturing a circle and thinking about that case. But yeah, you're right. We're looking at a wide range of curves.
So I think in the integrable case, even when n goes to infinity, you still see the shape of the curve.
Right. Right.
So do you have maximum principle for the porous equation also for other dimensions? So that should be dimension independent, right?
Let me see.
Some kind of statement like that.
Porous medium equation, of course, one still has the maximal principle in higher dimensions. However, the problem is in higher dimension, how do we justify the mean field limit? So I think for higher dimensions, even if you just try to do a formal argument, like doing this, then you have to involve some kind of sphere packing issues when you use the concept of a locally uniform distribution.
Well, I mean, you still get so you still get the third bullet point on this page. So in some sense, your functionals will converge to an integral like this, right?
That's true if you have this kind of locally uniform distribution, saying that for whatever high density region or low density region, your particles are always having a configuration which is like similar with another location. For example, they all have a hexagonal configuration. Then I think at least formally you can still derive this. But how do you know that it should have such a hexagonal configuration in a dynamical problem? So what I remember is that in the paper by Schlager, what he did is to require a very special assumption on the initial condition, so that the initial condition has this locally uniform distribution, and this can be propagated in time. So suppose your initial data is somehow some kind of hexagonal structure in 2D, then how do you propagate that kind of assumption in time? That could be very difficult, I think.
Yeah, also just from looking at Oldschlager's paper, well, anyway, yeah, I guess this is just a question of looking at specific paper, but he seems to be using S less than D. So I guess you're actually generalizing his results, right? Rather than just using them.
Yeah, his result is formulated in a slightly different way. But I think what I'm discussing here is kind of a special case of his result. So his result can include both the integrable case and the hypersingular case. Because he did some kind of cutoff of the singularity, and he tried to say how the cutoff is scaled with the factor here in front. I don't remember the detail, but something like that. So what we did here, we don't use his result directly, but we borrowed some of his ideas.
Right. Thank you.
Somebody else have a question?
So right. So to get to your result, you did have a variety of pieces. What have you found any parts along the way that do translate to higher dimensions? So I understand that at the moment the whole theory doesn't, but are there any points in particular that translate well to higher dimensions?
Let me see. I don't think so. Even this part is purely one-dimensional.
Okay.
So see, we have to cut it at here and at here. If you are in 2D, then where should you cut? If in 2D, instead of taking an interval, you have to take some bounded region and compute all the pressure along the boundary. So then it's not merely about 2 endpoints. It's just you need to care about what density you have on this whole boundary of your region. Then it's much more complicated than that.
Right.
So have some kind of Stokes theorem.
Yeah, so you need to care about what's the pressure on the boundary of that region, and also what's the normal derivative, so that's the forcing direction. And I don't know how to do that.
It's interesting because so I understand what you're saying about there being issues of local minimizers and on, like, let's just say the sphere S2, that you could potentially get local minimizers like evenly distributed points on a circle. But just thinking about it from the context of, like, I don't know, like electrons repelling each other and whatnot, right? If you put several electrons on a sphere, right, dynamically speaking, you would never expect them to just remain on a circle. So it's just, that is interesting. I wonder if
I think another possible direction is to put some noise on the system.
Yeah.
Yeah, but then I think for the noise, we haven't thought about that carefully. So for the noise, the first question one has to answer is, what should be the proper scale of the noise you want to put?
Right.
So if you put too much noise, then you will see the noise in the mean field limit.
Right.
Like a false medium diffusion together with a normal diffusion, then it just becomes a very different thing.
Yeah, that would be curious. Yeah, I was wondering if, like, if you had something where, like, I don't know, every like you had a periodic perturbation where all of your particles got, like, slightly moved in a random direction. If that would
Previously I have seen a paper by Sylvia Servati on the energy minimizer with some temperature. So what she did is something like for when you add some kind of noise, then there is scaling, so that once your noise is beyond that scaling, then it just destroys all the local configuration structures. Then you just have a very nice mean field description, something like that. But I didn't go into the details there.
Sure. Interesting. Thank you.
Thank you. Some more questions? Okay, when it's not the case, and thank you very much for a nice talk and question. Maybe we can stop.